We'll be talking about some of these properties, particularly the optical properties of the semiconductor nanowires. And in fact, though I am at the Bose Center, all this work has been done actually in Department of Physics, IIT Kharagpur, but I have had strong collaboration with some of the Bose scientists here and some of the results that we will show, so that makes some justification. Okay, so just to introduce, I don't have to say that nanowires or nanorods or nanocones, whatever I will say, these are all one-dimensional kind of a structures, and of course this is the definitions that both the carrier confinement and transport takes place in one dimensions. So, and the other important thing of the nanowire that you can always put it either in vertical topology or in horizontal topology. So that gives some advantage in terms of different kinds of devices. Like if you want to really make a fat kind of devices, horizontal topology is actually natural choices. But if you want to make a kind of a, trying to make a solar cells, trying to make a sensors, photo detectors, you can get a very, very high surface to volume ratio if you put in a kind of a vertical topology. So both can be done. And of course, you can use the horizontal case, particularly the optical devices, so-called the waveguide effect for optical devices. And as I said, that vertical topology will show a very, very superior anti-reflection properties, which you will show as the course of our lecture. The other thing is that you can really make junctions, different kind of homojunctions, heterojunctions. Either you can make a core shell kind of a junction, so there is some nanowires actually in the core, and there is something different materials in the shell, so that gives you heterojunctions. Or if you can have a very nice MB or CBD kind of technique, you can make PN, PN, PN. So either make a homogeneous PN junction or hetero PN junction or even a super lattice. So that is a great advantage for these nanowires. And particularly for the optical devices, this kind of things are very, very interesting, because you see that your typical nanowire core diameter is about, depends upon your growth, is about 30 to 50 nanometer, and cell thickness is not more than some 10 to 20 nanometer, which is much less than the diffusion length of the carriers, minority carriers. So that means if you are trying to go for a minority carrier devices, so carrier recombination is almost negligible, except there is a traps at the interfaces, so all of them are collected. So that gives rise to very, very high gain or responsibility in the detectors, which we will show in our talks. So a lot of people, these are some of the old slides actually. The leading group actually started from a Harvard group, Professor Charles Lieber. So in fact, he made all kinds of nanowires, making the PN junction, PIN junctions, making detectors, FET, lasers, solar cells, sensors, almost close the actually field, almost as far as the device making is concerned. So these are actually, as you see, mostly horizontal, and these are actually kind of a vertical structures. As I said, this is very, very interesting for making some solar cells, and yeah, this was reported there. So I will show that why it is interesting for making this kind of nanowires for solar cells. So this will be my talk outline. So initially I will give some of the results on silicon and germanium nanowires, because one of the main motivation of my research group to make silicon-based photonic devices, because as you know, the silicon, germanium, all they are very, very nice electronic materials because of their other electronic properties, but they are actually bad photonic materials because they don't have they have an indirect band gap in nature. So we'll try to see whether we can try to, avoid some of the problems and try to get some emissions or very good detectivity. And I'll show some of the actually silicon nanowires to silicon nanorods to silicon nanocones by making different kind of, growth. I'll not go into the growth details much. Then I will come to actually some 2,6 semiconductors like a zinc oxide, and it's very, very important or very popular semiconductor, and try to take some of the plasmonic structures, and if time permits, I'll try to show that these nanowires or nanorods can be made hybrid devices, which is very good for flexible devices. This, by the way, that actually one silicon photonic chip that has been reported in last year Nature. So you can expect in the next decade actually that silicon photonics will actually have a good share with the silicon electronics. So the density is not so good, but still it has got 50 to 60,000 components. So chip size is definitely much more compared to your computer chip, but it has got a very, very huge potential, particularly for to avoid a heating problem. So I'll not go to that today. Okay, so the question is that since silicon and germanium both are actually indirect band gap semiconductors, can we not make a lasers or a LEDs or detectors out of them? So of course, a lot of efforts are being done for the last decade at least. We have done a lot of work actually on germanium nanocrystals. So these are the normal typical route. People do either okay, either silicon nanocrystal or germanium nanocrystals. And as you know that if the size is less than the exciton pore radius, you get a strong quantum confinement effect. So you clearly see the size effect here in silicon nanocrystals, and the emission is somewhere in the visible to near infrared. This is of course the defect emissions. Otherwise, the people have tried also to create some kind of strain in this kind of a structure. So there are a lot of ways to make the strain. So one of the ways that make a micro bridge of germanium and put a high pressure. That is also people have shown that you can just by the use of the strain actually you can change the band gap. Why you can change the band gap? The reason is here. Particularly it is very good for germanium, not so good for silicon because of the reason. See, germanium is the indirect band gap material. So this is the indirect band gap transition from L valley to the top of the valence band. And this is the direct band gap transition from the gamma value of the conduction band to the top of the valence band. And this difference of energy is very, very small. It's about 0.1 to 0.15 electron volt. In the case of silicon, this difference is actually more than 2 electron volt. So it's very difficult to make a silicon showing a direct band gap emission just by strain. But in the germanium, it is possible. So that was actually shown by this group. Or even the latest one is that try to make a germanium tin alloy, because tin is a direct band gap semiconductor. On the other hand, if you put some of tin in germanium lattice, actually they are very, very strongly lattice mismatch. So you get a huge amount of strain. So that was done actually that whenever 8% of tin was included in the germanium lattice, and when 12% of tin was incorporated, it actually converted from a indirect band gap to direct band gap semiconductor. So this is just by strain. So that shows that there is a possibility of doing some strain engineering this kind of so-called indirect band gap semiconductor and get some direct band gap emission. So this is some of our results actually. In this case, we grew the germanium nanowires by a very standard vapor, liquid, solid kind of methods. This is not really the epitaxial germanium nanowire. This is done normally a tube furnace in the lab, but definitely we get germanium nanowires of about diameter in the range of 60 to 80 nanometer. And there is always an oxide in the top, all for the silicon germanium, the germanium oxide is in the top. And you get a Raman spectra which shows that there is a germanium oxide present on the top. So that is always a problem. But for the photonic devices, probably it is not a problem. It's a problem for electronics. And I don't want to go to the details of the Raman, but it shows some kind of compressive strain. The compressive strain, the value was not as much as that was shown in the other paper by incorporating tin. But when you take a photoluminescence spectra, we definitely see a very nice direct band gap transition, particularly at low temperature. As you see, the temperature dependent photoluminescence. If you say 10K, this wavelength actually, this is basically the direct band gap of germanium. Is about 0.8 electron volt. This is about 1500 nanometer. And indirect band gap is about 0.67 electron volt. So this transition is basically for the direct band gap, and this transition for the indirect band gap. So at very low temperature, between 10K to few hundred K, actually I see that direct band gap transition is very, very strongly predominated in this case. And as you increase the temperature, of course there is a lot of non-radiative recombination centers present. So phonon-induced transitions actually get dominated. So that's why when you go above some 200K or so, you only get a indirect band gap transition. The intensity of that is very, very low. So as you know, the quantum efficiency is very low. If you do a temperature, power dependent, and as you see that's what we expect normally. As you increase the temperature or decrease the temperature, there will be a shift of the PL peak. So that is clearly shown here for the direct band gap semiconductor. Similarly, for a direct band gap semiconductor, if you change the excitation power source, the peak position does not change. So this is also a good signature that all this transition comes from the direct band gap of germanium. So the question is that can we make a device out of that? I mean, can you show that it works as LED or the lasers? Photoluminescence probably is still a little bit easier. And of course, whether it works at room temperature, that is the greatest challenge. So we make actually a metal insulator semiconductor devices using this germanium nanowire and try to inject the carriers. So as you see that this is the IV characteristic of that device, that in the forward bias you can inject lot of electrons from the metal, and ideally they should give a recombinations to give some kind of emissions. It does not, actually all this yield that I will show here, it always act only on the forward bias. That is what is expected to do. But when you do the electroluminescence, as you see at 300K at the room temperature, the emissions from the direct band gap is almost negligible. Most of the emission comes from either from indirect band gap or a defect induced, in fact, more on the defect induced transitions or the phonon transition. But on the other hand, if you do at low temperature, as you have seen in the PL, you get a no phonon transitions from the germanium around the same 1500 nanometer that we have seen. And if we change the temperature, actually you increase the temperature, there is a red shift. But of course, the so-called the phonon induced transitions or the defect transition takes over at high temperature. So, and that's why actually the EL spectrum is very, very kind of broad. So, still not that useful to make some kind of devices, but it shows that there is a possibility that if you can really control the strain and if you control the defects in this kind of nanowires, particularly if these are if it actually grown, you can, there is a possibility that at least you can get a germanium nanowires based devices which are working near room temperature. Okay, this is some other, actually I have just shown, I don't want to go into the details of how this is made, actually this is very well known. You can also make either nanowire by a process called metal assisted chemical etching. So, it's a catalyzed, so this is the process that we do, the rest of the actual work that I will actually describe, where you have used the silicon nanowire actually which was etched by a process called metal assisted chemical etching. Either it can be done with the gold nanoparticles or silver nanoparticles. We have used gold nanoparticles and you get a very nice freestanding silicon nanowires like this. But on the other problem that if you make these nanowires and see from the top in the SEM, you can see actually all of them bunches together. So, actually all of them joins on the surfaces. So, what you can do some anisotropic etching on the top by a known called KOH, and you instead of nanowires you can make a nanocones. So, some of the devices that will show actually based on this kind of either nanowires and nanocones. Okay, the first device that we tried in way back in 2012 actually to make we started with a P silicon nanowire and N cadmium sulfide was grown just by chemical method, not any CVD or MBE. So, and it shows a very, very nice, actually it must show a very nice IV characteristics or junction characteristics, which I have not shown here. Since it showed a very nice junction characteristics, very low dark current, actually we have used this as a photodetector. So, all this actually is a photodetector either at reverse bias or at a zero bias. Okay, and we see that silicon, cadmium sulfide, silicon is a near infrared band edge. On the other hand, cadmium sulfide is a visible region, and you see this get a very nice broadband response of this detector, which works from about 0.8 electron volt to 2.8 electron volt. So, first is a very broadband detector. Now, what about the responsivity? That means how many actually photons were generated per, how many carriers were generated per incident photon. So, that is actually called the photoresponsivity, that means how much ampere per watt. And typical silicon commercial devices that you get from the market, this responsivity is about 0.5 ampere per watt. But as you see that in this case that we have, when you make these silicon and cadmium sulfide core cell heterojunctions, we already have a gain because the peak photoresponsivity that we get is about 1.37 ampere per watt. So, it's kind of a more than 200% gain for this kind of heterojunctions. That's what exactly we get when you calculate the external quantum efficiency. So, this gain comes from actually not from really the gain in the device, this comes from the actually extra electron injection from the so-called the cathode material, which has been shown by the band diagram here. So, this is actually this N-cadmium sulfide P silicons, you have got a conduction band offset and valence band offset, and of course that the myotic carrier from these electrons actually goes to the anode, and this electron mobility is much higher than the whole mobility of cadmium sulfide. The whole mobility of cadmium sulfide is very, very low. So, of course, there is always a kind of a electron accumulations. So, to neutralize this actually, so there should be no charge accumulations, lot of actual electrons are injected from the cathode material, that's why we get this kind of gain. So, this is not really the gain in the true sense, but on the other hand your responsivity is higher than the commercial silicon device. And the detectivity is also quite good enough. Normal silicon device is about 10 to the 12 joules actually. So, it's very, very comparable. So, that was for the bunch of nanowires. So, I didn't have a control whether there is a single nanowire or 2 nanowires. I don't show in ACM or TM because of the lack of the time. But then we thought that why cannot make single nanowire devices and try to see that we can increase the gain further or so-called the responsivity further. So, these nanowires, actually one of these nanowires that we grew by this chemical etching, took one of them, and this was done by the electron lithography technique in collaboration with Professor Rai Chaudhuri in the Bose Center. So all this E-beam lithography and photolithography, we took a single nanowire of silicon, put in a silicon dioxide substrate, and ultimately the detector that you are making is a metal semiconductor metal photodetector, okay? And your substrate is totally isolated because of silicon dioxide. And the diameter of the nanowire is typically two devices we have used. One is 80 nanometer, other is 100 nanometer. In fact, we have used a few, but we have got good results on that. And the electrode spacing is about 1.2 micron. Again, you should, this is not a junction, this is a kind of a photoconductor, metal semiconductor metal. So you don't get a so-called junction characteristics in the IV, but you get a so-called good optical switching characteristics. Either use a lasers or light source of different wavelength. So even at a 0 volt, you get a nice optical switching. And this is a kind of a power-dependent optical switching. This we have shown by the argon laser, actually, 540 nanometer. As you increase the power, of course, it should increase. That's what is happening. But of course, if you take a photocurrent as a function of power, it goes sublinearly. Because that is, of course, possible because you have still a lot of defects in the nanowires which are chemically etched. So there are a lot of interface traps or the surface traps. So the exponent value is 0.3. That shows these nanowires is not an ideal nanowire till now. Okay. But let us see that what is there actually so-called the photoresponse or the responsivity, the same way that I have defined earlier, this the photocurrent density by the optical power density, and from there you get a how much ampere per watt. And you see now it's a huge difference. It's now instead of talking of 1 ampere per watt or 0.5 ampere per watt, we are talking about some values of 10,000 ampere per watt, 20,000 ampere per watt. So it's a increase by actually 10,000, 20,000 times. And this is the device 1. The device 1 was actually 80 nanometer dia, and device 2 is about 100 nanometer dia. So two things are important. Why the responsivity is so high actually compared to kind of a commercial devices. So that comes from this equation actually. If you find out the gain of this is a, as I said, this is a photoconductor devices. If you take the gain of this one, this is actually that the lifetime divided by the transit time, and if you calculate, you can finally get something like this. So of course the mu and tau is constant. So what is varying is ELL. So first thing is that, as I said, there is no recombinations because my the nanowire diameter is much less compared to the minority diffusion length. Of course, there will be recombinations if there are some traps. That is there. And the electric field is very, very high. The nanometer diameter is very low. And as you see that, that's why the 80 nanometer diameter responsivity is much higher than 100 nanometer diameter. And L that we have kept is only about 1.2 micron. So if you reduce the L, actually the responsivity will go up very, very high. And you see that it almost works actually even at a 0 volt. The kind of a built-in voltage that you get in the metal semiconductor so-called junction, that is good enough to actually collect all the carriers and give rise to very high responsivity. So this is actually, you can say, kind of a very low power, ultra sensitive detectors, whether it can detect a single photon. Actually, if you want to detect a single photon, you have to go something like 10 to the 6 ampere per watt, which people are trying by other means. But I think when we reported, this was the highest sensitivity or responsibility for a silicon photodetector. Okay, this is also because of the geometry of this nanowire. Actually, whether you couple the light parallel to the nanowire or perpendicular to the nanowire, actually the sensitivity is different. That's what we have shown, that actually if you put a parallel to the nanowire, the photocurrent is highest. When it is perpendicular, it goes lower. So that means it has got a polarization selectivity. If you put the polar plot of these two nanometer diameter, you can see the one with a lower diameter has higher polarization sensitivity, and the polarization sensitivity or anisotropy that you have got is about 42% for 80 nanometer diameter. Now, as I said that sometimes when you make an arrays of nanowires, actually in the top actually they are joined together. So we made some nano cones, and the nano cones are actually very, very interesting for making solar cells. In fact, people are actually silicon nano cones and nanowires. Mobile? Yes. Sorry, yes. Right. Sorry. Yeah, the mod amplifier is there. That's right. Thank you. So, in fact, this is a new thing that is coming out. Actually, people are calling silicon as a black silicon. Normally, silicon is gray. So, when it is black silicon, means it actually absorbs all the radiations. So, ideally, black silicon should look like this experimentally. So as you know, in the solar cell, finally the surface is texturized, because we normally lose about 20 to 30% of the light just simply by reflections. And then the people put anti-reflection coating on the solar cells. But these anti-reflection coatings are actually, these are the oxides are typically anti-reflection coating. These are wavelength dependent, these are actually angle dependent, and of course the position of the solar sun actually varies. So none of this anti-reflection coating is a perfect anti-reflection coating. So of course the solution may be that people are thinking that if we can really texturize and really get a black silicon surface, that will solve some of the problems. So some proof of concept we have shown. In this case, silicon nanowires we have done by two methods. One is metal-assisted chemical etching that we have shown earlier, and this is done by another technique called inductively coupled plasma reactive ion etching. This is again a method actually which is known for silicon device fabrication. So all are actually compatible to making devices, and you get a nanowires. So what you do in fact that use different kind of powers actually of the so-called the plasma. And finally, we have seen if you use a 150 watt RF plasma, we get nicely vertically oriented nanowires to nanocones. And in fact, So the reflectance spectra is very, very interesting. Okay, this is not calibrated one, so the value may exactly vary. So value may vary a little bit, so don't take this value. So that's why even a plain silicon wafer normally is 30%, but it is showing about 35 to 40% here. In the entire visible range, the reflectivity is very high. So that kind of light is lost, or radiation is lost. But as soon as you make a so-called the nanocones or the nanowires of different powers, you see reflectivity comes down to the lowest value that we have got, about 1.5%, actually 150 watt etched plasma etched nanowires. But it comes down to a value of 5 to 6%. So this is the average reflectivity of this one. And this reflectivity for the chemically grown and the plasma grown is almost similar. It's not much different. As you see, that is almost same. And then we actually have grown the cadmium sulfide. So the same kind of heterojunctions where they want to make a photodetector solar cell. And even after actually coating the cadmium sulfide, the reflectivity and the average reflectivity is about 2%, which is much, much less compared to planar silicon. Now, yeah, sure. Yeah. So what you can do a kind of, what we did actually try to see that experimental data, and we did an optical simulation just by solving the Fenel's equation is a COMSOL multiphysics software. So we took a model, a very crude model. So basically it happens, as you know, the Fresnel reflection happens because of the mismatch of the refractive index between the ear and the substrate. So here actually is very, very high. So then we put what is the effective refractive index of the so-called the nanowire diameter, and what is the effective refractive index of the nanocones geometry. So we get a graded refractive index. And we see that for a planar case, you get a huge reflections because of interference effect or a strong fringing effect. So this actually reduces in case of a nanowire, and in case of nanocones, it is reduced. There is no fringing effect, and that's why you get a nanowire for the nanocones. Actually, reflectivity is so low in the range of 1.6% or below 2%. And this actually, the so-called the calculated or simulated results and the experimental results are actually very, very close. So that gives us the confidence this is a good material. Just want to give a proof of concept of the solar cell, but it was a very, very crude solar cell, so I don't want to compare the so-called the efficiency. Normally I should cut it off. But as you see that, compared to, because this geometry actually, compared to so-called the planar silicon solar cells, there is a improvement for nanocones grown by MSE. When you do the so-called the ICP method, actually the efficiency is much more, actually the fill factor increases. What I'll put, the external quantum efficiency is improved much higher when you can make a solar cell in this kind of devices. And why it is not good, in fact, for chemical etching nanowires, that was very, very clear when you measured the so-called the meiotic lifetime. We have shown actually the surface of the chemically grown nanowire, there are lots of defects and surface states. So that's why actually that so-called lifetime was very, very low compared to plasma grown or a bulk silicon sample. That was the reason the responsibility was so low. So I've got only a few minutes, so I'll be a little bit faster. The other thing that we took are the zinc oxide nanorods, in this case either nanorods or nanocones. And obviously this plasmonics is very, very well known that if you decorate it with different metal particles, you get strong localized surface plasmon resonance, and that gives rise to an enhanced absorptions of the light or enhanced scattering or trapping of the light. So if you can use this for making a kind of a devices, I will show this is the synthesis method. So what is interesting here actually, in this case the zinc oxide nanorod, we could show that normally zinc oxide is very good for using in the UV photodetector. So it works on the band edge absorption of zinc oxide. But as you are putting some gold or silver nanoparticles, you can tune that's what is expected here. If you make a photodetector, I have not shown the device here, pure zinc oxide you don't expect anything in the visible region. But since you have a strong plasmonic absorption due to the gold, in the visible region you get a good responsivity value or a good response. What you do in the infrared range, that means the ultraviolet range at the band edge of the zinc oxide. So the thing is not known. Why should it change when you make a zinc oxide to gold zinc oxide? Because most of the absorptions in zinc oxide is due to the band edge absorption. It's a direct band gap semiconductor. But here also the gold plays a nice role actually, that when you, this is actually zinc oxide, gold decorated zinc oxide nanorod, and actually that there's a, since there can be two kind of possibility. You don't know which one is really true. If you can, unless you do kind of ultra-fast spectroscopy measurements. One is this intraband transition of electrons from the gold D band to zinc oxides. So the number of carriers increases in presence of gold. That's why you get an increase in the responsivity. Or lot of that magnetic airs, the holes which are generated zinc oxide, these are actually trapped in the gold. So that also actually reduces the recombination probability. So both of them can contribute to the high responsivity of zinc oxide. I will not show this actually. We said this is multifunctional because we could show this zinc oxide acts as a very nice gas sensor at room temperature when you illuminate with light. And this is what is most interesting actually. Just want to show that when the gold plasmonic case actually it gives a very high sensitivity to the NO gas even at room temperature when you irradiate with a so-called the 550 nanometer radiations. So that's what we said multifunctional. I'll just take 1 more minute, Chairman, just to finish it up. This is a very recent actual work. A lot of work is now going on the bioelectronic devices which are transparent and which are flexible. Of course, India is now the rich in silk. Okay, these are actually called silk cocoon. Actually, this idea came when he was collaborating with one of the bioelectronics people. He makes this silk kind of a he extracts this silk from the trees and he makes kind of a silk materials. From there we made a silk film, and a lot of people are working throughout the world. Only few groups actually, 4 or 5 groups. In fact, we have demonstrated, this is a research work of thesis of Mr. Narendra actually. We showed a very nice resistive switching devices which is flexible. We showed a negative photoconductivity effect in these zinc oxide silk nanocomposites, which I will not explain today. But what is important here, actually we wanted to show here also that if you make a plasmonic zinc oxide nanorods in a silk platform, in fact we are trying to go for a flexible devices, but by the time what you get actually, this is the standard results which I have shown earlier, almost the similar kind of results. The responsivity is increased both in the visible as well as the ultraviolet absorption range. We get a very, very sharp transient pulses actually in the zinc oxide in these cases. And actually if you take this is actually that if you can do pulse measurements, and we have seen actually this is the zinc oxide silk with the gold nanoparticles. This is a pure zinc oxide gold, and of course these are nanorods on pure glass substrate. And these ultra-fast pulses actually that we get here in the photoresponse, this comes from the actually so-called the pyroelectric effect in zinc oxide. When the laser is incidenting zinc oxide actually gets heated, so you get either a positive pyroelectric coefficient or sometimes you get a negative pulse, you get a negative pyroelectric coefficient. So ideally this is something like that. You can in the future you can have smart textiles coated with this kind of devices, and finally they are self-powered because all these are actually taken at 0 volt. So I am sorry that I could not get much time to discuss on that. These are flexible, and these are actual devices on large area based on the silk platform. And silk is a very, very natural material and is a mechanical toughness which much more than most of the fibers, in fact highest among all the fibers. So that is one very good thing. So that's why probably silk sarees are so popular in India actually. So this works. And in fact, we are just comparing the so-called response with a reported kind of a flexible devices on different substrates, not on silk. And our values actually that so-called the photoresponsivity or dark to photo current switching ratio, which you could not show, is quite high. So really it could be used for a kind of a flexible photodetector on a bioelectronics platform or a field platform. So in summary, that we have shown that there is a possibility that if we can put lot of strain in germanium, either nanowires or film, by putting some kind of some other alloys or making alloys or putting some kind of strain, it could show. In fact, we got up to 225K. The highest reported in the literature is still 270K or something like that. These nanowire heterostructures are good for making a very, very broadband photodetectors, which works at a room temperature with a high detectivity or responsivity. Single nanowire has got a very good future for making ultrasensitive detector, which is very low power, and this so-called the black silicon, which is basically silicon cones, actually it could be very useful for making solar cells because they have a superior anti-reflection property, or even for the photodetector.